Well, let us continue our discussion on the Zeeman effect, and the Zeeman effect is actually, Zeeman spectroscopy is a whole family of experimental situations, and then there are specific names attached to various special features of the spectroscopic conditions which are different in different situations. So, then it is called as the normal Zeeman effect or anomalous Zeeman effect and the Paschen-Bach effect. So, essentially we reconciled with the idea that you have got the unperturbed Hamiltonian, which is the kinetic energy Hamiltonian and the potential energy in the field of the nucleus, and this is to be treated as the unperturbed Hamiltonian. The perturbation comes from an internal interaction which is ignored in the non-relativistic Hamiltonian, the internal interaction being the spin orbit interactions, because spin is an intrinsic angular momentum which the electron has, and this is then to be included as a perturbation. And then there is an external field, an external magnetic field, to which the atom would respond as if it had a net magnetic moment, and this magnetic moment would come from two sources. One is the orbital angular momentum and the other is the spin angular momentum. So, depending on the relative strengths of these two perturbations, there is a perturbation source mu dot b and the other is the spin orbit interaction. So, if the magnetic field is strong, then obviously the mu dot b would be stronger than the s dot l, the spin orbit interaction, and this is what is regarded as a, or it is called as a normal Zeeman effect, and this is just like a proper noun. So, it is like anybody's name as to why he has that name is, it is for historical reasons and for nothing else, not because it is normal and other phenomena are unusual in some sense. Then you may have a situation in which the magnetic field is of the same order, in the sense that it generates an interaction which is of the same order as the spin orbit interaction, and then you need to consider both of these together, and then you may have a situation in which the spin orbit interaction is really significant. This is what will happen if the applied external magnetic field is really extremely weak, and this is what is called as a weak field effect, and this is sometimes called as the anomalous Zeeman effect, and you will, as the discussion progresses, you will see why one is called, the first case is called as the normal and the last case as anomalous. So, that will become quite clear. So, let us begin with the strong field consideration, in which the interaction due to the magnetic dipole moment of the atom generates an interaction mu dot b which is much larger than the spin orbit interaction. So, this requires obviously a strong magnetic field, but then remember that the magnetic field is not considered to be so strong that b square terms become important. So, we retain our consideration within the linear phenomena which are linear in the magnetic field. So, it is strong, but not so strong as to consider the b square terms. Now, the unperturbed eigenfunctions, in which you must take the matrix element of the perturbation Hamiltonian, this is the cardinal rule that Sakurai talks about, which we have referred to, right. So, these unperturbed functions in this situation can be considered to be n, l, ml and ms, okay, because if the magnetic field was weak and the spin orbit interaction was strong, then J would be a good quantum number, J and Mj would be good quantum numbers, right, and not Ml and Ms, okay. So, the strength of the field determines what are the right quantum numbers to be used. So, in this case you will use the Ml Ms quantum numbers as generating the eigenbasis of the unperturbed Hamiltonian. This is not something you will be able to do if you are really dealing with very weak fields in which the spin orbit interaction is strong, okay. So, your good quantum numbers in this case are n, l, ml and ms, and the perturbation to be determined is then due to this magnetic field. The first thing you have to do is to get the interaction Hamiltonian, which is the mu dot B interaction, and you determine the correction, which is the first order perturbation correction in this unperturbed states, and you typically you could in the certain sense ignore the spin, but you do not really have to ignore the spin, because most of the situations that you come across, the common phenomena that you meet, do not require that consideration explicitly, as will become very clear now. So, this is the interaction now, and this mu has got two sources. One is the orbital angular momentum, the other is the spin. Remember that the g for the orbital angular momentum is 1 and that for the electron spin is 2. So, you have got the Bohr magneton. Keep track of the signs, there are two minus signs over here, okay, because mu is minus mu b, and this the first minus sign is coming from here, which is the interaction Hamiltonian, which is minus mu dot b. So, there are two minus signs over there and they cancel each other, and this is the correction that you really have to determine. So, this would be the consideration for the normal Zeeman effect, and this is what you choose to do because you work in the domain of strong magnetic fields, not so strong as to require the B square consideration, but strong enough to ignore the spin orbit interaction. So, this is what we have got. Now, if you consider B to be along the z axis, then L dot S and B dot S will give you Lz and Sz operators, right, and Ml and Ms are their eigenvalues, because Ml and Ms are simultaneous eigenstates of Lz and Sz. Okay. These two sources of angular momenta are completely independent of each other, and the eigenvalue of this B dot L plus 2s will be Ml plus twice Ms because of this consideration. I take B to be along the z axis. So, this is your energy correction, and Ms of course can take two values, which is either plus 1 or minus 1. Now, this is the correction now, and this correction depends on the sum of Ml plus twice Ms, and it does not depend individually on the value of Ml and Ms. Okay. So, various combinations of Ml and Ms which will give you the same value of Ml plus twice Ms, because you can get the same sum for different values of the individual components which go into the sum. So, you really have to consider the sum Ml plus twice Ms rather than the individual values Ml and Ms. Now, let us take an example that if you consider the 2p the Zeeman effect with the for the 2p electrons, then for the 2p L is equal to 1, Ml can take 3 values minus 1, 0 and 1, spin of course is half. So, Ms can take 2 values plus half and minus half, and Ml equal to 1 and Ms equal to minus half will give you Ml plus twice Ms equal to 0. So, it will not lead to any change in the energy, because the energy depends on this sum and this sum vanishes, right. Likewise, if you have Ml equal to minus 1 and Ms equal to plus half, and both the possibilities are contained over here. So, if you have this possibility, then again you will have Ml plus twice Ms equal to 0. Okay. So, in these two cases you do not have any correction for both of these combinations. So, in this case the magnetic field will not change the energy, and the degeneracy with respect to these quantum numbers will not be removed. So, what we are going to do is to first construct a table of various possible values of Ml and possible values of Ms, this should be Ms, and then we will construct the sum Ml plus twice Ms and then see what energy corrections come out of this consideration. So, this is our table, which is Ml, Ms and Ml plus twice Ms. So, Ml can take values 1, 0, minus 1, 0 and so on, and Ms can take values either plus half. So, the first 3 levels correspond to Ms equal to plus half, and the lower 3 levels correspond to ms equal to minus half, but these 2 levels are degenerate. So, although you see 5 levels over here, you are looking at 6 states, the 3 values of ml and the 2 values of ms will give you 3 into 2, 6 possible states, out of which 2 remain degenerate, right. They correspond to this combination ml equal to 1 and ms equal to minus half, and ml equal to minus 1 and ms equal to plus half. So, these 2 combinations, they remain degenerate and their energy is not changed, because the delta E for that is 0, ml plus twice ms is 0, and the remaining ones you do have an energy which is different from what you had for the original unperturbed eigenstate, which is Np, and you see that the spacing is proportional to the spacing between these numbers, and this spacing, the difference between these numbers is just unity. So, all of them will be equally spaced levels. So, you have equal spacings because of this reason, and the 6 degenerate levels split into 5 levels. Okay. These 2 remain degenerate and their energy also does not change at all. So, now let us consider only those levels for ms equal to plus half. This is just for our discussion, it is not that we are going to ignore ms equal to minus half, but we will find that when we consider ms equal to minus half we get the same result. So, to begin with, let us take a subset of these levels corresponding to ms equal to plus half. So, these are these 3 levels. You could also consider the other set corresponding to ms equal to minus half, which are these 3 levels. So, you take either the top 3 or the lower 3 levels, and then we will see what kind of splitting of the spectra takes place as a result of this. So, let us consider these states. For L equal to 2, you have this energy, and for L equal to 1 for principal quantum number n you have this. So, typically you would have a D to P transition, a D to P dipole transition in the hydrogenic atom. Now, if you keep this in a magnetic field, the mu dot B interaction will split the ND levels into 5 levels. Okay. These are the ones corresponding to ml equal to plus 2, plus 1, 0, minus 1 and minus 2. Likewise, the NP state will split into 3 levels, 1, 0 and minus 1 for 3 different values of ml, and then you can have transitions from the D levels to the P level, right. But now the single line that would have resulted in the unperturbed hydrogen atom splits into many, and you can see that there are a total of 9 transitions subject to these selection rules, because the dipole interaction is not going to change the spin. So, delta ms is 0, and we have considered only the ms equal to plus half states in this, right, because for the dipole transition the spin is not going to be changed, there is nothing in the dipole interaction which will influence the spin. And then you have transitions corresponding to delta m equal to either 0 or plus or minus 1. So, if it is equal to 0, these are called as pi lines, and if delta m is equal to either plus 1 or minus 1, these are called as sigma lines. So, the single line subject to these transition selection rules splits into these 9 transitions. However, out of these 9 transitions there are only 3 frequencies which result, because if you look at the differences, the difference between this and this remains the same, if because they are all shifting by an equal amount, okay, which is what we just discussed in when we were discussing the previous slide. So, there are only 3 different frequencies which result from these 9 lines, and these 3 frequencies are called as the Lorentz triplet. Okay, these were observed in the Zeeman effect, and you have these Lorentz triplet, and you could now consider the ms equal to minus half, okay, and do exactly the same analysis, once again you will find that the d2p for ms equal to minus half to ms equal to minus half with delta ms equal to 0, that single transition will again split into 9 levels, but again corresponding to the 3 different frequencies, which will be exactly the same as these frequencies. So, it really does not give you any new frequency, you get a net sum of a triplet even after the consideration of ms equal to plus half and ms equal to minus half. So, it is not that you have really ignored the spin. So, even if you do consider the spin, you get the same set of levels, and this is just what you would get if you were to ignore the spin. Okay? This is precisely what you would get if you were not even aware of spin, and in the early days of quantum mechanics when spin was not known, this is what was seen in the d2p spectrum, okay, and this was expected to be what should have been seen. So, it was called as a normal Zeeman effect, and it results not because spin has no role to play at all, but because it does not have any consequence on the appearance of the spectrum, which appears as a triplet. Now, this is the case for d2p, it does not matter whether it is d2p or also p to s. So, let us consider the other case. So, you have seen the Lorentz triplet in the d2p transitions, but if you consider the p to s transitions, okay, if you consider the p to s transitions, then again you would have 6 lines resulting from this, okay, but these 6 lines again correspond only to 3 different frequencies. So, you can do exactly the same analysis and you will find that only 3 frequencies appear, and it is for this reason that this high field or strong field Zeeman effect is called as the normal Zeeman effect, because most of the atomic transitions in the early days of spectroscopy were studied between the d and p states or p and s states, and in both cases you saw a triplet, namely the Lorentz triplet. In both cases it is not that the electron spin was hidden, but it did not have any major consequence on these sets of transitions which was studied in the early days of spectroscopy. So, this is called as a normal Zeeman effect. So, now we consider slightly stronger fields, so that b dot mu term is more important than the spin orbit interaction, but it is not so overwhelmingly strong that the spin orbit interaction is to be completely ignored at all. Okay. So, this is what is called as the Paschen-Bach effect, and in this case again ML, MS are good quantum numbers, and the reason these are considered as ML, that these are considered as good quantum numbers, because if the S dot L interaction was strong, if this right hand side of this inequality was stronger than the left, okay, then J Mj would be good quantum numbers and not ML MS. Okay. So, because the right side of this inequality is still the weaker one, okay, so this is still the less important term. So, we can continue to use ML and MS as the good quantum numbers, and in this basis we can find what the corrections are. So, what are the corrections to be studied? Now, the correction is due to these 2 perturbations. Okay. Now, we are not going to ignore S dot L interaction altogether. It is not so strong as to make ML and MS ineffective, making you require to use J Mj. So, you can continue to use ML MS quantum numbers, but you must take corrections due to both of these terms in this basis. Okay. And there are 2 contributors to the Paschen-Bach effect, and this is the superscript here stands for the Paschen-Bach Zeeman effect, because it belongs to the family of Zeeman effect, but this is a special consideration in which the 2 perturbations are more or less equally important. Nevertheless, the magnetic dipole term is more important than the spin orbit interaction. Okay. So, this is the situation which is under consideration for the Paschen back effect, and this is the correction due to the magnetic dipole term, and this is the correction for the due to the spin orbit interaction whenever L is not equal to 0. For L equal to 0, of course, the spin orbit interaction vanishes. Okay. So, L is not 0 in this case, and these are the two corrections that we must now estimate and get the correction to the unperturbed energy. So, let us proceed to get these. Let us first get the mu dot B correction. This is due to the magnetic dipole moment, and the magnetic dipole moment is because of the angular momentum coming from orbital angular momentum as well as the spin angular momentum. So, there are two sources, and the correction therefore has this L plus twice S over H cross dot B, and if you consider again B to be along the Z axis as we discussed earlier, you will get ML plus twice MS. This 2 is coming from the G factor for the electron, which is 2, and this is ML plus twice MS correction. So, you of course get an ML times H cross. So, there is an H cross which will cancel this H cross in the denominator, and this is the correction due to the magnetic dipole term to the Paschen back effect. Now, what about the spin orbit interaction? Okay. Now, this is the correction that we have to obtain. So, the spin orbit interaction we know from the Fourier-Wodzyn transformation of the Dirac Hamiltonian, it has got this explicit form which is xi r times L dot S, and L dot S is Lx Sx plus Ly Sy plus Lz Sz, and since you are taking the matrix element in ML MS states, Lx and Ly or Sx and Sy can be written in terms of the ladder operators, and if you did that, you will find that from the orthogonality of the ML MS states, they will not contribute anything to the energy correction. The only term that will contribute is the Z component, which is Lz and Sz. Okay. So, it is only the Z component which needs to be considered. These two components will not contribute anything to the energy correction, and now you have to get this Lz Sz. Okay. So, let us proceed to do that. So, Lz Sz, these two, this is a product of, this is a direct product of Ketz, right. So, it is a direct product of L ML S MS. So, you will get ML H cross coming from the operation of Lz and MS H cross coming from this. So, now you have got this correction for the spin orbit interaction. You now have to evaluate these space integrals, okay, because xi r has got this explicit form, and this space integral has to be evaluated to get the correction. Now, this can be easily done because you know the radial functions, and you also know that the potential goes as Ze over r or minus Ze over r. So, you have to take its derivative with respect to r. So, you get 1 over r square coming from this derivative, and there is a 1 over r over here. So, you need the radial integral of 1 over r cube in hydrogenic unperturbed wave functions, radial functions. So, these are the radial integrals which can be easily determined, since all of these radial functions are known, and if you evaluate these radial integrals, this is like getting the average value of 1 over r cube, and then you have got this ML and MS coming from here. So, if you take the average value of 1 over r cube, you get this term over here which goes as 1 over n cube, 1 over the Bohr radius cube, and then we have seen these terms earlier in our consideration of radial functions of the hydrogen atom. So, this is the correction to the Paschen back effect coming from the spin orbit interaction. So, let us rewrite this because it is nice to extract the fine structure constant out of this. So, put in the explicit value of A0, which is h cross square over me square, and this substitution gives you this h cross square over me square to the power 3 over here. So, we are just rewriting this expression with explicit expression for the Bohr radius, and then we extract the fine structure constant, because you have got E square over h cross c, you have got e to the power 6 here, e to the square here. So, you have got a total of 8 powers of e. So, there are 4 powers of e here and 4 over here, but by rewriting these terms in this fashion, you can write this as z alpha square. Okay. So, that is the advantage in grouping these terms in this form. So, again you can get the Bohr energy expression out of it, and then you find that the Paschen-Beck correction goes as z alpha square, then it is proportional to the energy. Do not forget the minus sign over here, because En is minus of this, right. So, you have got an En over here, and then you have got the L dependence here, you also have the ML and MS, and essentially this term together depends on both N as well as L. So, in a simple way, it is in a compact manner written as lambda with a subscript N and L, because it will depend specifically on different values of N and L, and then it will be proportional to the product, not to individual values, but to the product of ML and MS. Obviously, it will be 0 if either ML is 0, right. MS of course is either half or minus half. So, this is the perturbation energy correction, and notice that this depends on L, and the degeneracy with respect to the L quantum number is removed in the Paschen-Beck effect. Okay. So, this is our consideration of both the terms. So, now you combine the two, you have got two contributions. One is this contribution, the magnetic dipole contribution, the other is the spin orbit contribution. The magnetic dipole contribution goes as ML plus twice MS, and the spin orbit contribution goes as lambda times ML into MS. Okay. So, now you must add the two to get the correction, and this is where the fun begins, okay, because it is not trivial. So, you have to look at these two terms. This is ML plus twice MS, this goes as lambda times ML and MS. Okay. So, if you look at these two energies, if you have an excited state n prime and a lower state n, then you can have different transitions from n prime to n coming from these different combinations. So, you will have an excited state corresponding to n prime and a lower state corresponding to n, and you can have all kinds of different transitions, because one term depends on the sum of ML and MS, the other term depends on the product of ML and MS, right, and it is the same over here for the lower state as well. So, you can have very many different kinds of frequencies coming out of this, and if you look at transitions corresponding to the dipole selection rules, that delta m equal to 0 and delta m equal to either 0 or plus or minus 1, then these are the possible transitions that you can see, and they will result in a corresponding frequency shift, which is delta E over h cross, and all of these are observed in the so called Paschen-Beck effect. Okay. Now comes an interesting situation, that you have a weak field. Now, once you have a weak field, this term, the spin orbit interaction, is going to dominate. Okay. So, because the spin orbit interaction dominates, the unperturbed eigenfunctions must be considered to be eigenstates of j square and jz, and not of Lz and Sz. Okay. So, now the quantum numbers you must use for the unperturbed states are L S J M J and not L S M L M S. Okay. It is because now the spin orbit interaction is the dominant interaction, the magnetic field is weak, and therefore the dominant interaction is the spin orbit interaction. The good quantum numbers will be eigenstates of J square and Jz and not L square, not of Lz and Sz. So this is what is called as the anomalous Zeeman effect. It is in fact a rather common one and in some sense more important, but only for historical reason it is called as anomalous, because when it was seen in the earlier times it could not be interpreted when spin was not known. So it was only after Uhlenbeck and Goudsmit inserted spin in their discussion, and they got lucky because they had inserted it not on the basis of any physical understanding of the phenomenon, but out of what turned out to be a good guess, and later on it was rationalized in the Dirac theory, because it is essentially a relativistic phenomenon. So now your good quantum numbers are J M, and these you can express in terms of the ML/MS basis by expanding J M in the uncoupled basis of L and S, and these are the corresponding Clebsch-Gordan coefficients. Okay. So these are the eigenfunctions of L square, S square, J square and Jz, and this is the interaction Hamiltonian whose matrix elements must be determined. The Bohr magneton has got both of these components. So with the 2 minus signs you have to keep track of the term of both the minus signs, and now you consider B to be along the z axis. So out of the L dot B term and the S dot B term you need to consider only the Lz and Sz, right. But if you put in Sz and Lz, you are not able to operate on an eigenstate of Lz and Sz, right. So ML and MS are not good quantum numbers. So this is really the tricky part, okay, because ML and MS are not good quantum numbers in this case. So this is really the tricky part, but it can be handled using special techniques including the Wigner-Eckart theorem and some other aspects of the angular momentum algebra which we will discuss now. So this is what we have got. We have to determine this correction due to the term L plus 2s. L plus 2s is the same as J plus s, okay, because L plus s is J. So one of the s can be absorbed in J. So this interaction L plus 2s is effectively J plus s, and you therefore have to consider the matrix elements of this operator, which is the z component of J plus s, but in eigenstates, and these J and Mj is an eigenstate of Jz, no problem there, but this is not an eigenstate of Sz, okay. So for the first term Jz, you can operate by Jz on this and you will get Mj times H cross, but you do not get an eigenvalue equation with Sz, because this is not an eigenstate of Sz. So from the first one, from Jz, you get Mj H cross together with this H cross in the denominator, that H cross is cancelled, and the first term corresponding to this contributes this correction to the energy. The second term we have to figure out how to handle that, okay. So this is coming from the J term, and the net correction is now due to two contributors, one which is based on J and the other which is based on S, and now our question is how do we find this matrix element, okay. So, that is the question that we must address, and it is by no means a straightforward one. So, there are two alternative ways to get this. One uses certain vector identities and the other method uses the Wigner-Eckardt theorem, and we will discuss both of these because it is good to learn these techniques. And you remember here that you need the matrix element in JMJ state of a certain component of a vector operator. We do know that the angular momentum is a vector operator. Okay. So, our question boils down to how do you get the matrix elements in JMJ states of an arbitrary vector operator. If we can get it for an arbitrary vector operator, we can use that for the angular momentum S, which is also a vector operator. And now you will remember that in an earlier unit, I believe in unit 2, we defined what is the criterion that must be employed for an operator to be, for a vector to be a vector operator. And the criteria that we discussed were in terms of the commutation relations of the components of this vector with the angular momentum components. Okay. So, these commutation rules are equivalently how they transform under rotations, how the components transform under the rotations, and whether you study this response to rotation or study the commutation algebra, the both give you essentially the same results. They are completely equivalent as we have discussed in unit 2. So, this is the criterion that must be employed to recognize a vector to be a vector operator in quantum mechanics. And since we are dealing with a vector operator, we know that these identities are satisfied, and these lead to two additional identities, okay, which come directly as a consequence of these commutation rules. So, this is a matter of detail, you have to work out a little bit of algebra, but if you construct the cross product J cross V and add to it V cross J and use these commutation rules, nothing else, you will get that the right hand side is twice IH cross V. You already can see that if V is J, that is what you get, right. So, you have this identity, you have likewise another identity which comes from the same consideration, which is the second identity over here, and one of the techniques that we are going to use is based on this second identity, which is that this commutator is equal to what is on the right hand side, and this is an identity, it holds good for any vector operator V, it does not matter what it is, the only requirement is that it must be a vector operator. Okay. So, you check out if it is a vector operator, and in our consideration we are certainly interested in the matrix elements of the components of the spin angular momentum, which we do know is a vector operator. So, we will be able to use this identity. So, you now take the matrix element of both sides, the left side as well as the right hand side, in angular momentum states corresponding to the coupled basis, which is LSJMJ, right. So, because this is an identity, the matrix element of the left hand side is equal to the matrix element of the right hand side, and now this matrix element of the left hand side you can evaluate explicitly using angular momentum algebra. Okay. So, using angular momentum algebra, if you evaluate the matrix element of the left hand side explicitly, that is again a matter of doing a little bit of algebra, but you find that the matrix element of the left hand side vanishes. It does not mean that the left hand side of this identity is 0, it is not. Okay. It is only the matrix element in this particular case which vanishes, which also means that the matrix element of the operator on the right side also vanishes. So, you can now use that, so that the matrix element of this part minus the matrix element of this part vanishes, which means that the matrix element of the first term is equal to the matrix element of the second term. There is a factor 2 here and a factor 4 here. So, if you divide both sides you get this matrix element equal to twice of this. Okay. And essentially what you have is, using these identities, from the left hand side you have a j square operating on this, right. So, what happens when j square operates on this? J m j is an eigenstate of j square, the eigenvalue is h cross square j into j plus 1. Okay. So, that will come out and you will be left with the matrix element of V alone. Likewise, over here this j square can operate on the left, and again you get h cross square into j plus 1. So, you get h cross square into j plus 1 is a common factor, and you have to obtain the matrix element of this V and this V. So, twice of V, and then there is a factor of 2 on the right hand side. So, those will cancel each other, and on the left side you get the matrix element of V, on the right side you get the matrix element of this scalar operator V dot j and j, and now you have j operating on mj. Okay, that is good, okay, because we know how the mj eigenstates respond to the j operator. Okay. So, this is a useful thing, and this is what we need. With V identified as S, you are actually interested in only the zth component. So, you can extract that corresponding component which is of interest. You can also get this result from the Wigner-Eckardt theorem, and this is the result that we will use in our next class, but this result can be obtained also from the Wigner-Eckardt theorem, and I will like to discuss that technique as well, because these are powerful techniques and they have applications in various other spectroscopies, not just Zeeman spectroscopy, but in several other branches of atomic spectroscopy, molecular spectroscopy, or spectroscopy in condensed matter, and so on. So, these are nice techniques to learn. So, this is the Wigner-Eckardt theorem. This is the matrix element of an qth component of an irreducible tensor operator, and this is given by the product of a physical part which is contained in the reduced matrix element and a geometrical part which involves the Clebsch-Gordon coefficient, right. So, this is the Wigner-Eckardt theorem, and the Clebsch-Gordon coefficient under consideration comes from the coupling of j and k. And what is this j? J is the angular momentum coming from this right side, and k is the angular momentum like term which comes from the rank of the irreducible tensor operator. Okay. So, this is the Clebsch-Gordon coefficient that you would get if you were to couple j with k to get j prime, which is the angular momentum on the left side. So, keep that in mind. So, this is the Wigner-Eckardt theorem. Now, k being a vector, you are dealing with a vector operator, so the rank is equal to 1, and we will consider the angular momentum itself. So, we will consider, we will apply the Wigner-Eckardt theorem to the angular momentum. So, Tkq is jkq. So, we have written the Wigner-Eckardt theorem for the angular momentum operator. We have identified k equal to 1 here. Now, we have q equal to 0. We will consider a particular case. Q can be either -1 or 0 or +1. Okay. So, we will consider one of these, which is q equal to 0. So, let us take q equal to 0. So, I put q equal to 0 in this Clebsch-Gordon coefficient, and now I put q equal to 0 here as well. The corresponding component is the jz. So, you get the component jz, which is the one of interest. So, this is the matrix element of jz, and on the right side you need this reduced matrix element and the Clebsch-Gordon coefficient with k equal to 1 and q equal to 0. Okay. So, this is what you want. On the left side, Jm is an eigenstate of Jz belonging to the eigenvalue mh cross, and then from the orthogonalities of alpha and alpha prime, j and j prime, and m prime, you get these Kronecker deltas. So, the left side can be solved readily, and the right hand side you have got the product of the reduced matrix element and the Clebsch-Gordon coefficient. So, the question is, how do you get this Clebsch-Gordon coefficient now? Okay. So, this is the Clebsch-Gordon coefficient that you have to determine. Now, how would you determine that? you have to get the Clebsch-Gordon coefficient corresponding to k equal to 1, right. So, I have sent you the tables of Clebsch-Gordon coefficients, and we have also uploaded this at our course web page, and from that table, there are tables for different values of J2. The one which is relevant in our case, for the present case, is the one for which J2 is equal to 1, because k is equal to 1. So, we will take what is labeled as table 2 in the set of tables that I have given you. So, this is the table that you will find in what has been sent to you, okay, and this is also uploaded at the course web page. So, from this you have to find there are 3 into 3 9 elements, and one of these is what you want to use. Which one? So, the first thing to do is to notice that Q is our M2 and this is equal to 0. So, M2 equal to 0, so we must look at the middle column, right. The other thing you notice is that you have a delta JJ prime here, right, which means that J prime is equal to J, and in our case J is equal to J1. So, we must use the middle row, right. So, we must use the matrix element which appears at the intersection of the middle row and the middle column. So, this is the matrix element to be determined, okay. So, all we have to do is to plug in the values of M and J1 over here, and we will get this Clebsch-Gordon coefficient which can be inserted here, and then you can use this expression along with the reduced matrix element, okay. So, this is what you have to determine. This is the intersection of the middle column and the middle row, and you have to determine M over J1 root of J1 into J1 plus 1, but in our case we have, instead of Jm we have J prime M prime. So, this is just bookkeeping, and the Condon and Shorley notation has to be translated into our notation for the present case. So, our Clebsch-Gordon coefficient is M prime over root of J into J plus 1, okay. So, this is the coefficient that must be plugged in. So, this is what you get, alright. So, this is the left hand side, which is MH cross into these Kronecker deltas, then you have got the reduced matrix element and the Clebsch-Gordon coefficient, which is now evaluated explicitly using the Condon and Shorley table, and then this is M prime over root J into J plus 1. So, this allows us to write the reduced matrix element. So, you take this term and this term on the left side, okay. Now, this M and this M prime has to be equal, there is a delta M prime M over here, okay. So, this reduced matrix element must be equal to root of J into J plus 1 coming from here, H cross into these two Kronecker deltas coming from here, and the root 2J plus 1 coming from here when you do the cross multiplication, right. So, this is what you must get, and if you see Cowan's book, The Theory of Atomic Structure and Spectra, this is precisely the result that you will find. However, if you see Branstein-Jochid equation A453, you find this result, which is obviously different. What is the difference? The root 2J plus 1 is different because it can always be absorbed in the reduced matrix element, okay. If you remember, when we discussed the Wigner-Riccard theorem, we had mentioned that the Wigner-Riccard theorem is both a theorem and a definition. It is a definition of the reduced matrix element, and it is possible to incorporate the root 2J plus 1 in the definition of the reduced matrix element. So, you can include this, and then the two results are completely in conformity with each other, there is no contradiction between them. So, we will use this result, and this is the matrix element that we were interested in determining, which is the product of the reduced matrix element and the Clebsch-Gordon coefficient corresponding to k equal to 1, okay. Now, this is what we did for the angular momentum, what we want is for an arbitrary vector. Okay. This we get from the Wigner-Eckardt theorem applied to the vector operator V. And now if you take the ratio of these two, okay, the ratio is then completely equal to the ratio of these two reduced matrix elements. And notice that any further consideration of this result will be independent of the definition of the reduced matrix element, because in this ratio the root 2j plus 1 would go off. So there is no ambiguity coming because of that. So now you have got this ratio which you have found. So now the matrix element of the qth component of this vector operator is given by this factor here, right. This is the ratio which is some constant, and then there is the remaining matrix element to be determined, but this is the matrix element of the angular momentum operator. So this is the constant C which we have used. And now if you look at V dot j, because you had the matrix element of V dot j, right, that is the operator which we had to consider. So now you have the V dot j operator whose matrix element, and you can sandwich the unit operator in between. So sum over m prime going from minus j to plus j, j m prime ket bra j m prime gives you the unit operator. So I have sandwiched the resolution of the unity in between and then take the dot product of these two. So this is the matrix element of the dot product of two vectors, and this comes exploiting this resolution of unity in terms of the dot product of the matrix elements of the corresponding operators. So using this is the matrix element of V, which we know is a matrix element of J scaled by this factor C, and now this alpha dot j, this is the term that you want to determine, which is which we know over here is C alpha prime j prime. So we take particular values, we drop the primes here. So when alpha prime is equal to alpha and j prime is equal to j, you take alpha j m v dot j alpha j m in this case. So you can always take a special case of that to get C, because the value of C does not depend on the geometry, it does not depend on the azimuthal quantum numbers m. So you take a particular case, and for this case you have the same relation which holds good. Now j square operates on j m, giving you an eigenvalue h cross square j into j plus 1. So this gives us a value of C explicitly in terms of this matrix element divided by h cross square j into j plus 1. So now C being independent of the m quantum numbers, we can exploit this and we can use this value of C over here, because you are looking at the matrix element of the qth component of V, and now you have got this C, but the C is now determined explicitly in terms of this V dot j. So this result is called as projection theorem in quantum mechanics, and you will find it in Sakurai's book or in many other books. So this is the projection theorem, and using the projection theorem, if you now consider m prime equal to m, this is just a special case of the projection theorem for m prime equal to m. Now this is a relation which holds good for every component q. So if you add the three components and multiply by the corresponding unit vectors Ex, Ey, Ez, that relation will hold good for the vector as well, right. So you have got the matrix, this matrix element of the qth component, this relationship can be generalized to write the matrix element of the vector operator itself, and this is just the result that we had gotten earlier using the identities for the vector operators, okay. But now we got the same result using the Wigner-Eckardt theorem. So this is a result that we have got, and now we are interested in this because we need the matrix element of the z component of S, and our worry was that since the operand over here, which is this ket, is not an eigenstate of Sz, we had to figure out how to proceed. So, we have found a result which is going to be useful in getting this particular matrix element, okay. And we got this matrix element using two alternative procedures, one using vector identities and the second using the Wigner-Eckardt theorem. So, this is what we will do in the next class, which is to use this result which comes out of the theorem that I just mentioned, the projection theorem, and using this result we will figure out how to get the weak field Zeeman effect, because we need the matrix element of Sz over here. Questions?
Will contain Sz again, will contain Sz will be acting on the JMJ.
Yeah, we will handle it, but this is the main result which is going to be useful. So, in the next class we will get the complete expression. Any question? Okay, thank you.